Quantum computing. You've probably heard the term thrown around, promising to change, well, pretty much everything. But what is it, really? It can sound like something straight out of science fiction, but I promise you it's very real. And today, we're going to pull back that curtain and make sense of it all, from the seriously mind-bending physics to the real-world impact. Let's dive in.
Here's our roadmap. We'll start by going beyond the simple zeros and ones that power our lives today. Then, we'll get into the quantum superpowers that make these machines tick. After that, we'll look at the absolutely wild hardware needed to build one, face the huge challenges involved, and finally, figure out what these incredible computers will actually be good for. So to really get this, we have to start with the most fundamental building block of computing. You know, every single device you've ever used, your phone, your laptop, your car, it's all built on one simple idea: the bit.
Now, a classical bit is basically a light switch. It can only be in one of two states: on, which we call a 1, or off, which we call a 0. Simple, right? It's a binary choice. But a quantum bit, or qubit for short, plays by a whole different set of rules. Instead of being forced to choose between 0 or 1, a qubit can exist in a rich, complex combination of both states at the same time. And that one little difference, well, that's what unlocks an entirely new universe of computing power.
So, how in the world does a qubit pull this off? Well, it's not magic, it's quantum mechanics. There are two core principles that give qubits these incredible abilities, and trust me, they are genuinely gonna bend your brain a little bit. The first one is called superposition. The easiest way to think about it is to imagine a spinning coin. While it's spinning in the air, is it heads or is it tails? Well, it's neither. It's kind of both. It's in a state that contains the possibility of being heads and the possibility of being tails. Only when you measure it, when it finally lands on the table, does it collapse into a definite state. A qubit in superposition is a lot like that spinning coin. But, and this is a really important but, that analogy isn't quite perfect. In fact, as this quote points out, just saying a qubit is in both 0 and 1 at the same time is a super common oversimplification. The real story is actually way cooler. The proper way to say it is that a qubit is in a complex linear combination of its states. Okay, that sounds complicated, but think of it like mixing colors. You don't just have pure blue and pure yellow. You have this whole beautiful spectrum of greens in between. A qubit isn't just 0 or 1, it holds the exact recipe, the precise probabilities for what it will be when we finally measure it. That nuance is where its true power lies. All right. The second superpower is entanglement. And this is where things get really, really weird. Entanglement links two or more qubits together so they share a single, unified quantum state. Even Einstein was baffled by it. He famously called it spooky action at a distance. So what does that actually mean? Well, imagine you have two of these entangled qubits. If you measure one and find out its state as a 0, you instantly know with 100% certainty that its partner is also a 0. And it doesn't matter if that partner is in the next room or on the other side of the galaxy. Their fates are perfectly and instantly connected. Spooky is right. Okay, so we've got these amazing qubits with their quantum superpowers. But how do you actually build a computer with them? Well, it turns out the engineering is just as mind-boggling as the physics. Now, there are a few different ways to physically build a qubit, but one of the leading methods right now, the one used by companies like IBM and Google, is based on something called superconducting circuits. These qubits are basically teeny tiny electrical circuits made from materials like niobium and aluminum. At room temperature, they're nothing special, but when you cool them down, and I mean way down, they become superconductors. That means electricity flows through them with absolutely zero resistance, creating the perfect, quiet environment needed to create and control a fragile quantum state. And when I say way down, I really mean it. We're talking about temperatures around 20 millikelvin. That is just an impossibly small fraction of a degree above absolute zero, which is the coldest temperature theoretically possible in the universe. To put that in perspective for you, that is significantly colder than the empty vacuum of deep space. You have to go to these insane lengths to create a perfectly silent environment, completely isolating the qubits from any outside interference that could instantly wreck their delicate quantum state. And that brings us to the single biggest problem in quantum computing. You could call it the arch nemesis of every quantum engineer: noise. The process that destroys a quantum state has a name. It's called decoherence. And really, it's just a fancy word for what happens when a qubit loses its quantum superpowers. The second a qubit interacts with the outside world in any meaningful way, it decoheres. It snaps from that beautiful, complex linear combination back into a boring old classical 0 or 1, and all that precious quantum information is just gone. This definition really nails it. It's all about that physical interaction with the environment. That's the killer. So what exactly counts as the environment?
Well, it turns out noise can be almost anything. The tiniest bit of heat from nearby electronics, a stray radio wave from a cell phone, a microscopic vibration in the floor of the lab, even tiny imperfections in the materials used to build the qubit itself. Any of these things can cause a fatal error in a quantum calculation. So, after hearing about all these monumental challenges, you might be wondering, why are we even bothering? And that's a fair question. The answer is, if we can overcome these hurdles, quantum computers promise to solve problems that are literally impossible for any classical computer that exists today or that will ever exist.
We're not talking about the kind of problems your laptop solves, like browsing the web. We are talking about things like perfectly simulating a complex molecule to discover a new life-saving drug, or optimizing the entire global financial system in real time. These are what we call intractable problems. Problems so massive that even the world's fastest supercomputer would take millions, maybe billions of years to solve. A quantum computer could potentially do it in a matter of hours.
This all leads to a final and really crucial point about where this incredible technology actually fits into our world. Is it going to replace the computer sitting on your desk?
So let's ask the question directly. Is a quantum computer going to replace your phone or your laptop? The answer to that is a definitive and actually pretty fascinating no.
Think of it this way. Quantum computers are specialized machines. They're like a Formula 1 race car. You wouldn't use one to go get groceries, right? They're terrible at normal stuff like storing data or running a nice user interface. They are built for one thing, and one thing only, performing specific, mind-bendingly complex calculations. The real future is a hybrid one. Your regular classical computer will do all the prep work, feed the really hard part of our problem to the quantum computer, and then take the result back for storage and analysis. It's going to be a powerful partnership.
So this isn't a story about replacement, it's a story of an amazing new collaboration between two types of computing, and it leaves us with an incredible question to think about. As this powerful partnership finally comes online, what once unsolvable problem, what grand challenge that has stumped humanity for generations will we choose to tackle first?